Hello, this is Miss Meadows, and today we're going to look at metric conversions and how to use the metric system to convert between units using what we call dimensional analysis. The metric system is based on the value of 10, and it allows us to quickly convert basic units of measurement into more easily used numbers. The metric system is also known as the International System of Units, or the SI system. The SI comes from the French term Système International. The organization of the system falls into two parts: the name of the unit, which represents what kind of measurement you are making, and the prefix of the unit, which represents the size or magnitude of the measurement. For example, I can use a ruler to measure centimeters. Meters is the measurement of length, while centi is the prefix meaning 1/100th. So a centimeter is 1/100th of a meter. Measurements in metric that are common to chemistry. So these are the ones that we are going to see most often in this class. We have two groups shown here. On the left, we have direct measurements. Direct measurements are things like meters. Meters are a measure of length or distance, and we can use a ruler or a meter stick to directly measure that unit. A gram is one we will use a lot in this class, and grams measure mass, or how much matter or particles you have present. And we use a balance, which is typically an electronic balance, to find that. We also will use liters. Liters are a volume or amount of space that matter occupies. Typically, if we're measuring liquids, we will use a graduated cylinder or a flask to measure volume. But if you have a regular shaped object, like a cube or rectangle, we can also use a ruler because the volume is the same as distance cubed. So we could take the length times the width times the height and get our volume that way. Then we have on the right side calculated values. So there's no device to directly measure these, but they can be calculated based on other measurements. They are still considered metric units though, so we can still convert these between the metric units using prefixes. So the mole is a very important unit for chemistry, and it represents the number of particles. So if we were to count how many particles there are. It cannot be directly measured. So there's no instrument that's going to count our number of particles. So we measure things like grams and then convert it into moles. And then our last one is joules. This is the amount of energy in something. Again, we can't directly measure it. We can measure other things and then calculate energy using an equation. Metric prefixes. So why do we need prefixes? Let's look at an example to help us see why they're so important. So the apple shown on the balance below is recorded or has a recorded mass of 90.0 grams. So that's the mass of our apple. If we were to put 10 of those same exact apples on that balance, we would show a mass of 900 grams, so 10 times bigger. If we were to put 100 of that same apple, we would see a mass of 9,000 grams. So our mass just gets bigger. And again, if we were to put 1,000 apples, we would see a mass of 90,000 grams. So we can see as we add more apples, the numbers start to get very large and harder to report. It would be very easy to forget a zero and cause our data to be flawed. So as we get bigger and bigger measurements, or even smaller and smaller measurements, our numbers get a little harder to deal with all of these zeros. But the metric system is here to help deal with this. The metric system uses prefixes to show size without changing the number. So we're going to change the size of the unit we're using, but not the number we're actually recording. So let's see how that works. A prefix is the name of a metric unit, or in the name of a metric unit, describes how large that unit actually is. So let's see how prefixes can help with our data from our apple example. So in this table, I've taken the data we have from the previous slide on our number of apples and the mass of the apples, and those are in the first two columns. Let's take a look at the first row across. So if we took that one apple, we saw it measured a mass of 90.0 grams and grams are our base unit. So that's kind of like the basic unit. One apple is our basic measurement. So that's still just 90 grams. The abbreviation we're using is G for it. That's what represents grams, and it has a value of just 1. Now, if we went to the next line and we have 10 apples, the mass of 10 apples was 900 grams. So it's a bigger number. Well, if we didn't want to change that number, what we could do instead is add a metric prefix. So in the next column, it says 90.0 decagrams. So deca is a prefix added to gram to show us the size of that gram. So in the next column, we can see its abbreviation is DA for deca, G for gram. And then the value of it is times 10. So what deca means is that it's 10 times the amount of a normal gram. So if we have 90 decagrams, we have 90 times 10 grams. It's really what we're reading there. So instead of actually multiplying the number out, we're just changing what the unit tells us, which is a little easier. All right, let's look at the next one. We've got 100 apples, so 9,000 grams. So instead of putting 9,000 grams, we could use a prefix that means times 100 instead. So 90 hectograms, or Hg, is the same as 9,000 grams. Hecto means times 100. And our last one that you might be more familiar with is in terms of prefixes. If we had 1,000 of our apples, it weighs 90,000 grams. We have a lot of zeros there, easy to drop one and mess up our number. So instead of doing that, we can put 90 kilograms, or kg, and that means the same as 90,000 grams, because kilo means times 1,000. It's 1,000 times bigger than a gram. So when, say, large amounts of product, like somebody selling corn grain or flour or, big bulk items like that, they don't want to measure in grams because they're going to have these huge numbers. Instead, they can do it in kilos or kilograms and cut their number down, but still represent the same amount of substance by putting that prefix on it. So we can see that using the prefix, the number stays manageable, and the prefix just tells us how much bigger the actual measurement is. So what if the numbers are smaller, though? Does this still work? So we're going to take our apple and look at it in a little different way. So prefixes can also help with very small numbers. So let's imagine our apple, and we're going to start cutting our apple into smaller and smaller pieces, okay? They're always going to be equal pieces. So let's take a look just at the first line across the top. It says the number of apples, we got 1 apple. The mass of that apple is 90 grams still. And we're not going to cut it into any pieces. We're going to keep it whole. So the mass of all the pieces together, it's just one piece, is 90 grams. And if we were to go to after that big bold line, kind of focusing on one piece at a time. So the mass of one piece, since it's still 1 apple, still 90 grams. Metric prefix doesn't need one, and its value is 1. So that's kind of our baseline, base unit. Now, if we look at the next line, we've still got our 1 apple. It has a mass of 90 grams. But what if we cut it into 10 equal pieces? If we have all of those pieces together, in that fourth column, it says the mass of all the pieces is still 90 grams, because it's still all 1 apple. But if we were to take one of those pieces and measure its mass, it would be 1/10 of that, right? It'd only be 9 grams for that one little piece. So instead of saying 9 grams, what we could do is add a prefix. So in the next column, the metric prefix for the mass is 90 So we're keeping that number, 90 decigrams. So deci is the prefix that means 1/10. So we're dealing with 1/10 of our apple. So we have 1/10 of the grams, which kind of makes sense, right? So we have 90.0 decigrams. So deci means 1/10. If we were to keep going, our next line, that third one down, says if we had our one apple, weighs 90 grams. If we were to cut it into 100 equal pieces, so we're getting small apple pieces now, all the pieces together would still be 90 grams. But if we just took one of them, it would weigh only 0.9 grams. We're getting much smaller here. Well, if we didn't want to change that number, we want to keep the number the same, we can use a metric prefix, and one of those pieces would be 90 centigrams, because centi means 1/100th, just like cents in a dollar, right? We have 100 cents or pennies in a dollar. So centi means 1/100th. And the last example down here is we took our one apple, weighs 90 grams, but we were to split it and cut it into 1,000 equal pieces, which seems crazy to me. I don't even know that we could cut that, but imagine we did. The whole thing together, all the pieces would be 90 grams, but if we took out one of them, it would only weigh 0.09 grams. Pretty small piece of apple. Well, again, if we didn't want to change the number, we can change the prefix, because we start getting these small decimal numbers and it's easier to drop a zero and mess up our value. So instead, we can measure 90 milligrams. Milli is the prefix that means 1/1000th. So that little piece of apple, it weighs 1/1000th of the whole apple, because we cut it into 1,000 equal pieces. So that's how this kind of works. We're taking that unit, we're breaking it up into smaller pieces. Those pieces, if we kept them all together, would still weigh the same mass. But if we separate out one of them, it's going to be 1/10th or 100th or 1,000th of the mass of the whole thing. Okay. All right, prefixes and base units. So due to the use of prefixes, we can use the same measurement for very large and very small values, which means something like grams we can use for really big amounts of mass, or we can use it for really tiny amounts of mass. Same with liters, joules, meters, all of our different base units. And then here in this table are all the metric prefixes that we have. The ones highlighted in yellow are the ones we're going to see the most. And we're going to take a look deeper at that on the next page and how they relate together, how we use this information. But notice in the middle here is the base unit. So it represents 1. So this would be like your base unit of grams, liters, meters, joules, all of that, moles. And its exponent is 0, so 10 to the 0 is just 1, so it's all just equal to 1. Now, as we go up on the table, you'll notice that it's a multiplier, okay? So if we go to, say we're looking at a base unit of grams, we could go to decagrams, and that would be 10 times as big, or hectograms, which would be 100 times as big. Kilo is one that we're more familiar with. So a kilogram is 1,000 times bigger, or 10 to the third power, of the base unit, or 1,000 grams. And we can keep going up. Some of these you might recognize as we get higher, like mega, giga, tera. We use those a lot with storing data in bytes. So we have megabytes, gigabytes, terabytes of data storage. So we see that a lot more, right? We want to store a lot of data on our devices. So we need these very large prefixes that we use. Now, if we start back at our base unit and we go the other direction, we are getting smaller. So we're taking that base unit, we're breaking it into pieces and looking at the size of one of those pieces. So, for instance, a decigram would be 1/10 of a gram, okay? And that's 10 to the negative 1 power, right? A centigram would be 1/100th, just like a cent is 100th of a dollar, right? 1 penny. A milligram is 1,000th of a gram, and we can keep going down. You'll see over here that there are some different things to give you some references on why we have some of these tiny ones. The size of an atom, so if I was looking at the size of a carbon atom, the diameter of it is 0.1 nanometers. So instead of writing 0.00000000001 meters, all those zeros that we have to deal with, instead we write 0.1 nanometers. And it's a lot easier to interpret, to type, to write, and understand. As we get even smaller, we get into the size of the nucleus. That's where we get into femto. And then the electron size is atto, is the prefix. So you can see this is why you have these really tiny, tiny things. It's because of our size of our atoms. Now the same can be true with our kilo. Instead of writing something like 10,000 grams, having to keep track of all those zeros, we can just write 10 kilograms and still communicate the exact same information without having to write all the zeros. So we have kind of two ways of simplifying numbers in science. We can write them in scientific notation to not have to write all the zeros, but we can also change their unit prefix, and that can help us in writing things in a more simplified way. So both of those are great tools for us. Like I said, the ones in yellow are the ones we're going to be using. So we'll take a look at how we use those on the next slide. So when we're doing a metric conversion to change from one unit to another, say I give you something in kilograms and you need it in grams, we need to know the relationship between those. And that was shown on the table, but sometimes it can kind of be confusing when we get into the smaller units. So this is our prefix relationships, all right, on the left side, and these are some examples of adding them to their base unit. So in the blanks here, we can put a base unit. But it's going to be the same on both sides. So I could say 1 kilo of something, of whatever the base unit is equal to 1,000 of that base unit. So for instance, 1 kilometer or 1 kilometer is 1,000 meters. And we abbreviate that as 1 km equals 1,000 m. So m for meters, k for the prefix kilo. So we do need both of those pieces to communicate the information properly, both the prefix and the base unit. Now, when we get into these smaller ones, on the previous slide it said centi was 1/100th of the base unit. But if we have one of the base unit, we're not looking at 1 centi, we're looking at one of the base unit, then we need 100 centi to equal the same amount. Just like if I have $1 and I want to compare it to pennies, I need 100 pennies to equal $1. That is the exact same idea right here, okay? Now, if I'm just talking about the value of a penny is 1/100th of a dollar. A single penny is worth that. So we need 100 pennies to equal that dollar. So we need 100 centi to equal 1 of whatever the base unit is we're looking at. So if we're looking at grams being our base unit, we'd say 100 centigrams is equal to 1 gram. And again, we abbreviate things 100 cg for centigrams equal to 1 g for gram. Similarly, milli is the same way, but it's 1,000. So 1,000 milli blank equals 1 blank. We need 1,000 of that small unit, that prefix unit, to make one of the base unit. So 1,000 milliliters is 1 liter. We'll probably use this conversion the most out of every conversion in chemistry. We do a lot between milliliters and liters, so that's a good one to just know, right? And then the last one that we will run into, we will look at nano. We will use the nano prefix, and it comes into play when we're looking at the length of a wave of light. That's the biggest time we use it. So if we look at this is 1,000, million, this is a billion. So a billion nano blank equals 1 blank. So a billion of the nano units are equal to 1 of the base unit. Okay, so we'd say a billion nanometers equals 1 meter. Okay, if we took a meter stick and broke it into a billion equal pieces, that would be a nanometer. Now we'd abbreviate that as nm for nanometers and m for meters again. Notice how similar that is to this up here for kilometers and meters, right? We just changed the K to an N, and now we're communicating completely different information here. Now, we don't ever write it out like this or type out those zeros because we're more likely to make a mistake. We use scientific notation. Now, you could write it as just 10 to the 9th. You could also write it as 1 times 10 to the 9th. They mean the same thing. So instead of writing 1 and all those zeros, we write 10 to the 9th, and that's going to equal to our base unit. So in this case, we'd say 10 to the 9th nanometers equals 1 meter. And this is really the only one we're going to use for that prefix nano. We're going to use it in meters because, like I said, it's measuring the wavelength of light, and length is in meters. So that's where we run into that one. Centi is probably used the least out of these, but we want to be aware of it because it can pop up. So those are our major metric prefixes. All right, now we're going to look at converting from the base unit into something with a prefix, a metric prefix. So given a value in a base unit, we can convert it to another unit of the same measurement. So if it's in grams, we can go to something with a prefix in grams. And we do this by multiplying or dividing by multiples of 10. So we saw on the previous slide that everything is based on 10. We're looking at tens, hundreds, thousands, millions, billions. It's all based on 10. So everything we multiply and divide by here is based on tens or multiples of 10. So we're going to look at each of these examples separately. So our example says, what is 783 meters in kilometers? And then in centimeters. So that's two separate questions we're going to do. So when we set up a metric conversion, we're going to use what we call the railroad track method. Hopefully you remember this from your honors chem class. And basically it's just a method of setting up our values and showing how the units change. It's called dimensional analysis. This is really important in chemistry, and we use it in all kinds of different conversions. So understanding it here will make other conversions much easier. And yes, you do need to show work and be able to do this method. So 783 meters is our given amount. That's what we have, and we want to change it first to kilometers. So in our little T-chart in our railroad track, we're always going to start by putting our given amount, 783 m for meters, in the top left corner. It's just our starting point. And then what we want to do next is get the meters, because we don't want those anymore. We want them to cancel. So we're going to place m in the bottom right corner so that those are one's on top, one's on bottom, and that will allow them to cancel out with each other. And then on the top above that, we want the unit we're trying to change to. So in this example, we're trying to change to kilometers. So we're going to put km for kilometers. And then we need to look at just this right side of our little T-chart here. So we've got km over m, kilometers and meters. We want to know what the relationship is between kilometers and meters. So to decide that, the first thing that we do is decide which one's bigger. So thinking back to that chart we had, we want to go with the one towards the top. So kilo is bigger than our base unit, meter. So whichever one's bigger, we're going to put a 1 next to. Then we're going to think about the relationship. So a kilo means 1,000 times bigger. So if the top says 1,000 meters, essentially, because 1 kilometer means 1,000 meters, we want the bottom to also show that. So 1 kilometer is equal to 1,000 meters. So we think about the relationship there and think about which one's bigger. We put a 1 next to it, and then how many of the smaller one does it take to equal that 1? Next, we want to do our math. So the way these are set up is so that it's essentially a math problem. It's setting up fractions and these what we call conversion factors. But it does it in a really clean way so that all we have to do is multiply our numbers on the top and divide our numbers by any number that appears on the bottom. So if we were to read this, I would take 783, multiply by 1, then divide by 1,000. Well, when we multiply by 1, it doesn't change our number. So we have 783, we're dividing it by 1,000. You can do that in your calculator. If you're comfortable doing those calculations in your head, you can do that too. So a kind of simple way when you're dividing by multiples of 10, like 1,000 is a multiple of 10. Really, when you're dividing by those, you're moving the decimal from the number to the left, however many zeros appear there. So we have 3 zeros in 1,000. So really, we're moving our decimal to the left 3 places. 1, 2, 3, because we're dividing, we're making the number smaller. So our value should be 0.783. And then we've canceled out our meters because they're on the top and bottom, and we're left with kilometers. So we get 0.783 kilometers. So if you have 783 meters, it's equal to 0.783 kilometers because kilo represents that 1,000. It's a bigger unit. So our number should get smaller. All right, we're going to do a similar problem, but now we're going to look at centimeters. So we're going to convert our same 783 meters, but this time into centimeters. So we're going to go ahead and set up our t-chart again. We're going to have our given 783 meters in the top left corner. And just like the previous one, we want to go ahead and put meters on the bottom to make sure that they will cancel. So we design it in the way to actually make them cancel. And then we put the unit we want on the top, which in this case is centimeters. So C for centi, M for meters. And it's always good to leave kind of, you notice I put my units towards the right side of my little t-chart there, way over on the right, so I've got plenty of space to write my numbers. Now, we're going to focus in on that right side and we're going to decide our relationship. So first thing we want to decide is which one of those two things is bigger. Is a centimeter bigger or a meter bigger? Now you can think back to our table with all the prefixes in it and think about which one's bigger, the centi or where the base unit was. Well, the base unit is higher on that list, so that's our meter, and that would be the bigger one. So the bigger one gets the 1. Now we want to think, how many centimeters do we need to make a meter? So centi represents 1/100th, okay? So it's 100 times smaller than a meter. So it's going to take 100 centimeters to equal 1 meter. Now that we've filled in our numbers, this is when we can do our math. So we're going to multiply across the top, divide on the bottom. So 783 times 100 divided by 1. Now again, we can put it in a calculator, or you can also think of moving, since we're multiplying, we want to move the decimal place to the right, and we want to do it 2 times, so we have 2 zeros. So essentially, we want to add 2 zeros to the end of this number, since our decimal is right here. So when we do that, we get 78,300 centimeters. Okay, so that 78,300 centimeters is the same or equal to 783 meters. Okay. All right, we're going to do 2 more examples. So we're going to be given a value with a prefix and convert to our base unit in this first one. And again, we can do it by multiplying or dividing by a multiple of 10. So it's the same process. We're going to start with our given. So what is 426 milliliters in liters? So our given there is 426 milliliters. We're going to put that in the top left corner. We want to get to liters. So first we're going to copy down the unit, ml, milliliters, to the bottom because we want it to cancel. We're going to put liters on the top because it's what we want. Then we're going to think about the relationship between the two on the right side. So thinking about our chart, is the base unit liters bigger or is milliliters bigger? Milli. So our base unit is bigger. In this case, milli is 1/1000th. So since milliliters are smaller, we want to think about how many of those it takes to make a liter. Since milli means 1/1000th, it's going to take 1,000 of them to make a liter. Again, we want to do our math. So multiply on the top, divide on the bottom. So 426 times 1 divided by 1,000. Again, we can think about, since we got 3 zeros there, we want to move our decimal place 3 places to the left. So 1, 2, 3. So we should get 0.426 liters, and our milliliters will cancel, top and bottom. Okay, so going from a prefix to a base unit or base unit to prefix, it's the same process. We just have to think about really how that relationship works on the right side. Which one's bigger? How many of the other unit do we need to make it? Now, the last example we're going to do is how do we convert when both of the units have a prefix, okay? And this is a little bit different. You can see in my railroad tracks here, this is why we call them railroad track, because you can just keep adding on to them. When we need them, it's a little bit longer, we have more space in there. And it's because we don't know, I don't know off the top of my head how many centimeters there are in a kilometer or vice versa. I don't know that. I don't want to memorize too many things. It's too many relationships. I want a few simple things that I can keep kind of in my toolbox and pull from when I need them. So what I do know how to go from kilometers to meters. I'm going to put M up here for meter. Okay, so I know how to go from here to here. I also know how to go from meters to centimeters. Notice that both the terms have meter in them. That's our base unit. So I know how to go between my base unit and something with a prefix. So this is like the path we're going to take. So when two things have a prefix, we're going to go to the base unit first, the meter, then we're going to go to the other unit. All right, so let's look at how that works out in our calculation here. So we have 1.3 kilometers and we want to find centimeters. So again, we're going to put our given amount, 1.3 km for kilometers or kilometers, on the top left corner. We're going to copy the kilometers to the bottom because we want them to cancel. Now, since we've got prefixes on both, we're going to go to the base unit first. They have meters in common. That's our base unit. So we're going to put M on the top. Okay. So now we're going to focus in on just the center section. Meters and kilometers, which one's bigger? So hopefully by now you're seeing that kilo is our biggest one. That's going to get the one next to it. And kilo represents 1,000 times bigger than something, so it's going to take 1,000 meters to make that kilometer. So now, but we're not going to do any math yet. We're just setting things up. But we can see that our kilometers would cancel out. So it kind of helps us ignore them if we go ahead and cross them out. So now, if we were to just look at this next part, we've got meters on the top. We still want to copy them to the bottom. We want those to go away. And what we want in the end is centimeters. So now we're going to go from that base unit to our unit with a prefix centimeter. So now we want to focus in on that right side all by itself. Doesn't matter what was written before. Centimeters and meters. Which one's bigger? Hopefully you're starting to see that meters are bigger, and it takes 100 centimeters to make a meter. Okay, again, we can cancel out our units. We can get rid of those meters, and it allows us to just have our units that are left over, centimeters. So now we want to do our math. So we're going to multiply across the top, divide by each number on the bottom. So again, there are ones on the bottom, so really that's not going to change our value, but we are going to multiply. So 1.3 times 1,000, so that moves our decimal to the right 3 times. And then we're multiplying by 100, so that moves our decimal 2 more times to the right. So we're moving our decimal 5 places to the right. We should end up with 130,000 centimeters. Okay, so anytime you're seeing something that both the units have prefixes on them, but they've got that base unit in common, we're going to go to that base unit first, because that's what we know how to do, and then we're going to go from the base unit to the other unit we want. Okay, it just kind of breaks up the question a little bit into chunks. That makes it a little bit easier. So hopefully in this metric system PowerPoint, you were able to see that the metric system uses base units to indicate the type of measurement. So liters indicate volume or grams indicate mass. We are using prefixes. They're used to determine the size of the measurement, so how small it is or how big it is. So kilo is very big, milli is very small. And combining these, we can express many measurements and eliminate the use of extra zeros. We can convert between these units using what we call dimensional analysis. So what we saw with the railroad tracks, that's a fancy name. Railroad tracks is really called dimensional analysis because we're analyzing the dimensions or measurements in our unit. All right, thanks guys.